if a real function f of x is positive, continuous, and decreasing for x greater than or equal to some integer n. So as we can see, that's true for this function. And an is a function of the integer n. So this describes the terms in the series. Then the series summed from n to infinity, and the integral from n to infinity of the real function both converge or diverge. So this can be visualized here. So if we look at this as the left Riemann sum, you have this rectangle with a height an according to this series, and these rectangles all have widths of 1 when you're incrementing n by 1 in this series. So the integral gives the area under the curve described by f of x from n to infinity, and that's smaller than the area given by the series. So therefore, if the series converges, then the integral that gives the smaller area also converges. And conversely, if the integral diverges, then so does the series. Let's determine if the following series converges using the integral test. Well, from this series, we can define a function that's positive, continuous, and decreasing from 1 to infinity. So therefore, we can integrate this function with respect to x. And because this is an improper integral, we can take the limit of a dummy variable and replace infinity as follows. And now we can evaluate this integral, which gives the arctan of x from 1 to b, and then take the limit. So what we get is the following limit of the arctan of b minus the arctan of 1. So remember, when y is equal to the arctan of x, we can take tan of both sides, and we can rewrite tan as sine y on cosine y. So if x approaches infinity, then y must approach pi on 2. So therefore this term evaluates to pi on 2, and this term is finite, so therefore this integral converges. And because this integral converges, this series also converges by the integral test.